this is not a baseball. This is a tennis ball, but it's kind of like a baseball. So let's say there's a fly ball and it's going out to the outfield, and you're standing somewhere and you need to move to catch it. Can you do that? Well, a lot of people can, and they do. And they don't calculate they don't use physics, right? They don't say, okay, where's the ball going and calculate where it's going to land and move there. Instead, they move in a way to kind of look at the motion of the ball and they end up in the right place. And so I want to model that with Python. That's what we're going to do. This is actually called the optical acceleration cancellation. Yeah. Method of catching a ball. And is this the way humans do it? Maybe. They've done some studies on that, and people looked at baseball for a long time. But the thing that's important to realize is that humans do not use projectile motion calculations and determine where it's going to land and then go there. We don't do that. I couldn't do that in 5 seconds. That's how long a ball might be in the air. Okay, so we're going to start off, we're going to model this. The first thing that we want to do is to just make a model for projectile motion. So I'm going to do this in VPython. So I want to start with a ball right here and a catcher, a player. And I'm going to launch the ball some initial velocity v0 at some angle theta, and then it has some mass m, and it's going to go like that. I want to just don't worry about catching it. I just want to make the ball move. When you build something, you got to start somewhere. And so let's just do this. So in this case, I'm going to calculate the force on the ball while it's in the air. That's going to be mass times gravity, and then I can say the net force is equal to mg, where g is the vector 0, negative 9.8, 0 newtons per kilogram. And I'm going to model this numerically, even though you don't have to. You could calculate the trajectory exactly. So I'm going to say, if I know the net force in some short time interval, this net force is the change in momentum over the change in time. So let's say delta t is 0.01 seconds. Then I can say, at the end of that time interval, P2, I should say P equals mv. P2 is P1 plus F delta t. Right? That comes straight from solving this. If this is P2 minus P1, that's the change in momentum. If I solve this for P2, I get that. Now I can use the definition of average velocity and do the same thing. I'm skipping over this because I've done this before. I could say R2 equals R1 plus P2 over M delta t. This is the average velocity, is the change in position. And R, I'm using R for the position. This would be my vector R. Actually, this is RB. I'm going to use a different R in a little bit. And then I update the position, and then I just update time, right? T2 equals T1 plus delta T, and then I go back over the whole thing again. And so let's do this. Let's build this in Python, and then we'll come back and we'll add this apparent acceleration calculation. Okay, so here we are. I've already got this started because I don't want to take forever. So normally I use Trinket to do my coding. This is GlowScript. It's the same thing. It's the same code, but the one difference between Trinket and GlowScript, Trinket gives you a side-by-side view of the code and the output, which I like a lot. But when I zoom in, we don't always get that. The other thing I really like about Trinket is that I could give you a link to the code. With the link, you can edit and run the stuff without even having to log in. In this case, if I give you the link, you can see it, but you can't edit it unless you copy it and paste it in your own account. So I don't know. I don't know which one's better. Let's just move on. Okay, so let's just see what I have right here. I have my vector G. In GlowScript v Python, it's Python with some built-in objects. It has vector objects built in, it has spheres, it has boxes, and I'm using spheres and boxes here. So I made the human a sphere, and when I make a sphere, I give it a position value, I give it a radius value, I give it a color value. Now I can give it other attributes. In this case, I gave the human a velocity. vector, so human.v, and I give it an acceleration vector, which I'll change these later, but right now the human's just going to stand there. The ground is an object called a box. It's a built-in object that has a position, which is the center of the box, and then the size is vector x versus y versus z. Z comes in and out of the paper. And I made it green because, it's grass, it's a football field, it's a baseball field. And then I made a ball, also a sphere. Now I put it, where'd I put the human? I'll put the human at 20 meters to the right of the origin, and the ball starts -25 on the ground. I made the radius really big. It's that big just so you can see it. And make trail mean when it'll leave a trail when it goes by. I gave it a mass. Here's my launch angle theta, and here's my launch velocity, 25 meters per second. No units in this stuff. And then so here's my initial ball momentum. It's the mass times velocity, but then I need to find the x and y components of the velocity. So this is not what I really want to focus on. I'm just trying to get it to work. Okay, so now let's say t equals 0, dt equals 0.01. And now I want to say while ball.pos.y is greater than or equal to 0. Right, so I'm going to model this as long as the ball's in the air. Once it gets back down to the ground, I want to stop it. The next line I'm going to put in here is rate 100. So this says since I have a time step of 0.01, rate of 100 means don't do any more than 100 calculations per second. Okay, so that would make it look like it's in real time. Now the first thing I can do is calculate the gravitational force, the net force. I'll just say F equals ball.m times g. Right, and notice here that g is a vector, m is a scalar, but this is going to be a vector value. And that's good because now I'm going to treat the force as a vector value. Now I can update the momentum. Ball.p equals ball.p plus. Someone once said, oh, you got to put spaces in there. So let's see if I can put spaces. I can't type that way, though. Ball.p plus f times dt. That's to update the momentum. This is a make equal to sign, not an algebraic equal sign. So this is take the old momentum, add the force, and make that the new momentum. So I don't need P1, P2, P3, P4. I just need P, and I'm going to change P. Okay, now I need to do the same thing with the position of the ball. Ball.pos, that is R. That's RB, right? That's the vector location of the ball with respect to the origin. Equals ball.pos plus, I'll write it like I did, ball.p divided by ball.m. That's the velocity times dt. And then update time. T plus dt. I can't write that way. Okay, let's run that and see what happens. I think it'll work. There you go. So there's my ball, baseball. There's no air resistance. I did not add air resistance. We can add that in later. There's my player, and it misses, right? Okay. So next, I want to plot the apparent position of the ball and the apparent velocity and acceleration. I'm going to do all those things. So let's switch back over to paper and see how you calculate that stuff. So paper view, not pay per view, paper. Okay, so let's get a new piece of paper. And I'm using purple because my black marker is bad, out of ink. I need some more markers. So let's define, here's the ball in the air, and then here's the human. The first thing, and this is the origin, so I have the position of the ball, RB. I have the position of the human, RH. And then I have this vector, which is what I want, R. R is going to be from the human to the ball. So I could say R is going to be RB minus RH. And so as this ball moves, that R is going to change. But what is the apparent position? So let's say I get a red marker and I have 1 meter this way and 1 meter, and I measure the height above that it is 1 meter. So I have this right triangle here. Right, so that's how high it appears to be. And I'm not actually using the angle because I don't want that. I want this actual distance. That triangle is similar to this triangle. Right, they're the same shape. So this triangle has a component of R dot ry, the y component, and Rx, the x component. So if I do this, y over 1, this is 1 meter, y over 1 meter, y apparent equals ry over rx. Now if I multiply that by 1 meter, I get the parent position, y apparent is just going to be ry over rx. Okay, let's plot that, and then I'll come back and we'll talk about the apparent velocity, because really we want the acceleration to be 0. Okay, going back to computer. Edit this. Okay, so I have my human. Human.pos is the location. So the first thing I can do is calculate r. And I'm going to move this down like that. So let's say r equals, just like I said, it's going to be final is ball.pos minus human.pos. And so r is a vector. Okay. So I can calculate the parent position. I'll call this the parent height. It's the parent height. Ya is going to be equal to the y component of r, so it's r dot y, divided by the x component of r dot x. And that's actually going to be, so r in this case, the way I drew it, r is actually going to have rx is going to be negative. So I think I want to put a negative sign in here so I can have a positive position. Okay, because my x component is negative. Okay, let's just plot this. So go up here, and I'm going to say G1 equals graph. Let's not give it a title. Let's just say the x title is going to be equal to time. I'll just do it shorthand notion. And then the y title is going to be equal to ya, the parent position. Now I need to plot on that. So I'm going to say let's say FYA. Let's call it GYA. I'll give a tutorial on graphing later. This is going to be G curve. That means it's going to be a curve. I need to say which graph is plotted on. So, because I'm going to have more than one graph. Graph equals GYA. And then I could give it a color, but I won't. So then down here, let's give it, let's make this width equals 500, height equals 200. That's because I'm going to have more than one graph. I want to make sure it's small. So down here, I calculate my position. I just need to plot it. So I'm going to say FYA.plot TYA. Let's see if that works. Let's see. Okay. So this is my apparent position. And you'll notice that as the ball passes overhead, this blows up, right? Because at some point, the ball gets completely overhead, then it appears to be an infinitely high position, right? Because I'm dividing by 0. I mean, it doesn't get to infinite because I skipped that step. I didn't do every single step. I can fix this graph. Let's do this just to make it look a little bit better. So I'm going to say if YA is less than, let's see the magnitude. So the absolute value of YA is less than, let's say, 5, 7. If it's less than that, then plot. Otherwise, don't plot it. Let's see what happens then. Okay, so now it's going up. It's going to blow up, and then it's going to, and then I stop plotting and I jump down here because then I have a negative right now. Now on the other side, the r.x is positive, and I have a negative value over there, so that's why it flips there. But I'm pretty happy with that. Okay, so but what we want to do, we don't really care about the parent position. I care about the parent velocity, and you can see here that the velocity is very low, but then it's going to speed up because that's the slope of this line. So how do I calculate? I could take the derivative of my function and get an expression for the velocity, but I'm instead going to do a cheat. Okay, so let's go back over to the paper and think about this. So here is my ball. Here's my human. And here's my ball. And so I can calculate Rx and Ry, and that's my Rx, Ry. That gives me my apparent position. And then a little bit later, it's going to be right here, and so I have a new apparent position. So if I knew my old y value and my new y value, I could say V apparent is going to be delta y apparent over delta t. So what I want to do is to say this is going to be y apparent minus y apparent old, the previous one, divided by delta t. And that's what I'm going to do. So since I'm changing this y, I'm changing this every time. So I need to kind of temporarily save the old value and calculate this, then update it. So let's do this. This is a little cheat. Where did I go back over here? Pick computer. Okay. So let's go down here. There's my R. And here I'm calculating YA. Now I want to calculate the velocity. So let's say this. YA old equals, no. Let's just go up here and say YA old equals 0. I'm just going to give it a number. If it doesn't work too perfectly, that's fine. So there's my YA. Okay, I have YA old. Now I'm going to say VA, that's the apparent velocity, is going to be equal to the change in Y, YA minus YA old, divided by dt. Now I can update my old value. So I'm going to say YA old equals YA. So what I do is I use my old value, I use that to calculate my velocity, and then I'm going to use that to update my velocity in my old position. Okay, so let's do that. Now let's plot the velocity. So I want to go up here and let's make a new graph. GVA equals G curve. I want the whole, this is a copy of this whole thing. Okay, the title, this is called this VA, and let's call this V, and call this V, and call this V. Okay, so now down here I have my velocities. Let's just plot that, and if they get too big, I can change that later. So let's just say FVA.plot TVA, and let's see what happens. Okay, so that's my velocity. It's going to blow up. Okay, again, let's put a limit of like, let's do the same thing. And we don't really need to do that. I'm just doing it. I have no idea why. So I'm going to say if ABS VA is less than, I'm going to say 4, then plot. Okay, so it's increasing, right? This is there, it jumped down. So, but here the key here is that let's go ahead and let's put the human at the landing location and see what changes. That'll be useful. And this, I could probably change this down to 3. Let's change this down to something smaller, to like 3. Okay. But what I'm going to do actually is go down here and say print ball.pos. This is going to tell me the final position of the ball. Let's change this to 3. Let's change that to 3. Okay, so I want to find out where that lands. And you could calculate where it lands. You could use the range equation, stuff like that. But I mean, I'm running the thing, I can just print it out. And then I'm going to put the human at that location. Okay, so this is my final position. I only need the X. Let's put the X. 37.6. So go up here. I'm going to change my human location to this. Now let's watch what happens to these two curves. Okay, so it's going to hit, and I'll show you that in a second. But now, oh, that is decreasing. That's kind of, well, it's not decreasing much. Yeah, so I'm pretty happy with this. This is a fairly constant velocity, right? It didn't change hardly at all. So if, and you can see that in the position up here, if the person is at a catch, this has a constant velocity, which would be 0 acceleration. So if the person moves in a way to make the apparent acceleration 0, then they would catch the ball. And you see up here, they did indeed catch the ball. See that? Ball caught. Okay. So now we need to calculate the apparent acceleration. So we're going to do the exact same thing here. I'm going to say y v old equals 0. Again, that may not be true, but I don't really care. And then down here, I'm going to say, let's say the apparent acceleration is the change in the velocity. So I have the VA old. What did I add up here? Yeah. YV old. So it's going to be VA, the new velocity, minus the old velocity, which is V. YA old. YV old. Yeah, that's fine. Minus, what did I call it? YV old. Divided by dt. So that's my new acceleration. Once I've done that, now I can update my old velocity. YV old equals VA. And let's plot that. So I'm going to make another graph. And call this AA. Call this GAA. FAA goes on the graph AA. Okay. Let's just run it. I didn't plot that one. GAA equals graph. Where's my graph? FAA, GAA, AA. Did this not show up? Where's my other graph? Why didn't it make the third graph? GAA is graph. FAA. Well, that's fine. I don't know what happened there. So now, but I want to move my person with that acceleration, unless it's not calculating the acceleration. Oh, I never plotted it. I didn't plot it. That's why. So let's say FAA dot plot TAA. That's why I didn't make it. There it is. Okay, so you see here, that does have a 0 acceleration. Now let's move the ball back and let's just see what that acceleration looks like. So here's a short shot. So I'm going to put, let's put this up here at 37.67. Just remember that. So let's put this back at 20. So it's going to go overhead. And you'll notice the acceleration is not 0 down here, right? That's not 0, and it does blow up. That's fine. I'm not even going to fix that. Now, if I throw it too far, the acceleration would be also not be 0. So I want to move in a way such that the acceleration is 0. So here's what I'm going to do. So I have the human. I can move the human with some velocity. Let's just do that. So I'm going to say, I first need this thing, and I've actually played around with this already, so I know what to do. Let's call this A scale equals 100. This is the linear scale relating the acceleration of the human to the apparent acceleration, right? If I can't use the actual apparent acceleration, that wouldn't be fast enough. So I'm going to then say human dot A equals A scale times vector AA 0, 0. So now I'm going to give the human an acceleration that is equal to that value. Now, it could blow up, and I don't want the acceleration of the human to be infinite. So let's put a cap on that. Let's say if the acceleration of the human, so mag human dot A, is greater than 5, then let's make it 5. So I'm going to say human dot A equals 5 times norm human dot A. So the norm is a unit vector in the direction of human dot A, so that will give it the same sign as before, right? So if I'm accelerating that way, I'll still be accelerating that way. And now let's do the same thing for the velocity. Because I don't want the human to run too fast, right? Well, we can leave that off, but let's say the human can, if human.mag, human.v is greater than, I used 8, then human.v equals 8 times norm human.v. So then again, we put a speed limit on both the acceleration and the velocity. Now I have a velocity and I have an acceleration. So the first thing I'm going to do is update the velocity of the human. So human.v equals human space human.v plus human.a times dt. And then I can update the position. Human.pos equals human.pos plus human.v times dt. Okay, let's just run this and see what happens. Okay, so here you'll notice the human's moving back. We'll look at the graphs in a little bit. And I did not calculate the position of that person. Boom, caught it. Let's do this. I already know where that should land, so let's print human.pos, the final position of the human. Okay, let's see. Nailed it. Okay, and then let's look at these. So the graph, so you see here that the acceleration is 0 until the very end. The velocity, the parent velocity does change a little bit towards the end, which is kind of strange. But this is still fairly constant. Okay, that would be right, because it doesn't have, if the person was in the same spot for the whole time, then these would be fine. But they're not. So the person needs to move to make the apparent acceleration 0, and that's what they did. The parent acceleration was at 0 at each instant. Okay. Let's make the ball go short. So let's say the initial velocity of the ball is 25. Let's make this 70, and let's make this 18. Let's see what happens there. So now the person has to move in, right? Because the acceleration's negative. I don't know if they're gonna make it. I think I have my. Oh, that's pretty close. They just weren't going. They weren't able to go fast enough to get to that. Okay, that was an uncatchable ball. Let's turn this to 21, so make it a little bit easier for the person to catch there. And this is in 3D. Caught the ball. Okay, I'm going to do one more thing, and then I'm going to let you have this code. This is the part that I really like. What if, let's put this back at a higher speed, let's say 27. Let's just make sure it works. Because that's a pretty high fly ball. The person's not really moving at all. I think it's just going to hit that person. No, they are moving. Okay, they caught it. Okay, what if there's air drag on the ball, right? If I want to have a ball with air drag, then it's really difficult to calculate the location of the ball where it's going to land. I couldn't just calculate it and go there. That's not an easy problem to solve. But in this case, it still works. So let's go ahead and add air drag situation. So I'm going to say the net force is the gravitational force pulling down with the backwards pushing drag force. So I need the density of air, 1.2. I need the size of the ball. I'm just going to say it's pi times, it's not an actual baseball. I'm going to use like, choose a radius of, let's say, 4 centimeters. Pi times 0.04 squared. Drag coefficient of a sphere is 0.47. Why do I know that? I've just done this so many times. So I can use 1/2 rho AC V squared as the drag force. So now down here, I can say that the force is going to be this, the gravitational force, minus 0.5 times rho times A times C times the velocity squared, so I can say mag ball.p divided by ball.m. That's the velocity. I need to square that. Now that's not a vector. I need to multiply by the unit vector of the momentum so that it's in the opposite direction. So times norm ball.p. Oh, and let's see if this runs. We should be able to see that it's not a parabolic path, and it's not going as far, right? And the person's gonna have to really hustle to catch it, and they're not gonna make it. Okay, let's give the person a chance. Let's lower this angle to, let's say, 50. And let's see if you can tell if it's not a parabola. Oh, they're not gonna make it. Oh, I think they could catch that. They made a dive for it, right? They made a dive. But you'll notice this is not a parabola. It's not. This side is going down more than that one does. Let's give that a little bit higher velocity. Let's say 33. I think they're going to catch it. Caught the ball in the hand like that. Okay, so I'm pretty excited because it actually works. I mean, this is not necessarily the only way that humans work. And also you'll notice that I only did motion of the person. They were already in line with the ball. If you want to modify this program, put the person anywhere and have them move, I'm not sure exactly how you would calculate that, but you can think of a method for that. Another thing that you could use as homework is, what if you launch a bunch of random balls and just see how many of them he catches? Or her. It could be a gender-neutral ball right here, a human sphere. So there you go. That's how you use the optical acceleration cancellation method of catching a ball. And that's it. I'll give you the code. And I did write a blog post on this for Wired. It's not out yet, but when it is out, I won't post this video until that's out, and then I'll include a link down below if you want to read that. But this has more details, so talk to you later.